Hello everyone, and thank you very much for your interest in our work. I'd also like to start by thanking the organizers for this opportunity to present. So I am Paul Kent from ORNL, and today I'm going to be presenting some of our work using quantum Monte Carlo methods to look at excited states of 2D nanomaterials and solids. And besides showing some of the successes we've had, I'm also going to point out some areas where we've had to develop new methods where the current methods haven't been quite as accurate as we had hoped. First, by way of acknowledgements, I want to thank the US Department of Energy Basic Energy Sciences for funding. This work is done in the context of the Computational Materials Sciences program, and I'd also like to acknowledge the Insight program for our computer time. Perhaps most importantly, though, I want to thank all the co-authors and members of the Center for Predictive Simulation of Functional Materials that I direct. And as you can see here, besides Oak Ridge, we're at Sandia and Argonne National Laboratories, also Brown and North Carolina State Universities. So besides this talk, we've made quite a number of other contributed talks at this conference. And so if you are interested in learning more about quantum Monte Carlo, I would just recommend you put in quantum Monte Carlo into the search box and take advantage of one of the benefits of this hybrid conference to go back and watch some of the other talks. So the outline of this presentation is really quite straightforward. I'm going to give a general introduction to quantum Monte Carlo, point out some of the challenges and progress that we need to make to advance the methodology, and then spend most of my time describing really two projects. First, looking at the excited states of 2D germanium selenide, and then to tip my hand a little bit, we'll then spend some time looking at the properties of lithium cobaltate, where standard methods are not going to work quite so well. So this is more the work in progress, but we've got some new methods there that look really very promising, both for increased accuracy, but also improved insight. And then, of course, I'll conclude. So a little bit about quantum Monte Carlo methods. So this is a very general term for stochastic solutions of Schrodinger's equation. There are, of course, quite a few quantum Monte Carlo methods. And the main one that we're going to be using here is real space diffusion quantum Monte Carlo. And in this approach, all we do is take a trial wave function and propagate out the ground state wave function from that, subject to some constraints such as the nodal surface of that trial wave function. As we will see, this is a very accurate approach, even in sort of the standard formulations that we use today. And one of our main reasons actually for being very interested and excited in the approach is that there's really very few approximations that are made, and importantly, they are now increasingly all testable. One of the ways they're testable is that these methods are generally, at least, variational in the energy. So if, for example, we can get a better trial wave functions, we'll get a lower energy, and we formally know that is a better solution. These methods can treat strong electron correlation. They treat van der Waals effects very well, and they're applicable to a wide range of systems, so isolated systems through to periodic metals and insulators, so condensed matter. Note we've just added spin orbit implementation, for example, and of course it's very convenient that these methods map well onto modern computers. I would note actually there's actually quite a few publications that I'm aware of on systems of hundreds of electrons just using departmental resources these days, because the compute power we have locally is increasing all the time. It's really only when one does very large numbers of electrons, heavy elements, or ask for really small error bars that the costs really increase. And so just as a reminder, we're going to be doing Monte Carlo here. So we have the Monte Carlo convergence with 1 over the square root of the number of samples. So to halve an error bar, a statistical error bar, we need to pay 4 times as much in compute power. All of our calculations are done using the open source QMCPACK code, and I highlight that here because actually late last year we had a workshop, a virtual workshop, where we produced over 10 hours of videos that are now up on YouTube, tutorials, and also a virtual machine. So if you are interested in trying out Quantum Monte Carlo, you can now download this and actually try out the workshop exercises, for example, without having to go through and install all the software yourself. So the link here is there for more details. And just as an example, towards the end, we had a tutorial on actually applying spin orbit or molecular calculations. So a very recent development and improvement in the methodology. To give some context for our work, one of our goals is that we should eventually be able to assess all the sources of error in our calculations so that we know we're reporting the correct properties for all the correct reasons and not just some happy accident. And of course, that means there needs to be progress in solving the correct Hamiltonian using accurate Schroeder potentials, for example. Spin orbit needs to be included, or at least an option for appropriate systems. And then some points that I'm going to be highlighting in this talk, we need to solve on a sufficiently accurate geometry of the material or molecule. And then also our wave functions need to be accurate enough. So just to illustrate that, there's no point us doing a calculation with an extraordinarily accurate ground state wave function, only to follow that up with a calculation for an excited state, which is much less good and higher in energy than it should be, because then when we compute the energy difference for the excitation energy, we will get poor results. So all of these need to be worked on, particularly for systems where the mean field methods that we might use to generate the trial wave functions or the geometries today, systems where those might be unreliable or not trustworthy in some way. So let's now move on to our first major topic. That is our investigation in 2D germanium selenide, and more generally the Monochalcogenides. And like a lot of 2D materials, there's huge promise in these materials for a broad range of applications and realizing a large number of physical properties in these 2D materials. And of course, we would like to be able to predict the properties accurately and reliably for them. So what then is the structure of these materials? Well, sort of viewed from the top, we have a fairly regular mesh, but viewed from the side, we see that these are not planar materials. There's this sort of zigzag up, down structure. So there's quite a few geometrical parameters. And this, of course, might be a concern in terms of predicting them, because we would expect there to be significant van der Waals in this material, particularly when we consider multi-layer systems, for example. One of our reasons for interest in this material actually is that besides there being current experiment on these materials, there is also conveniently bulk data available that we can use for validation studies. I'd also like to highlight actually that in addition to a germanium selenide study, a different group studied gallium selenide with similar methodology and actually made many similar conclusions. So we have sort of different independent efforts working on these materials now, and the methods have been quite successful, as I'll try to show. So then how do we do the bulk validation, and what sort of methodology are we following? So I've got some details here of the calculations. These are relatively standard for current Quantum Monte Carlo calculations. So we use BFD potentials that were developed for Quantum Monte Carlo calculations. Our trial wave functions actually come from a plane wave calculation, although in QMCPACK we're going to convert those into real space splines for efficiency. We have a fairly small time step. We do twist averaging, and we actually go up to over 1,000 electrons. What then do we find when we look at bulk germanium selenide? So we do the diffusion Monte Carlo. For example, here's total energy versus volume. We also look at excited states, and we're going to come back to that in a moment. And in this sort of table, I show the lattice constant, bulk modulus, and cohesive energy for sort of a menu of different approximate DFT functionals, and also the diffusion Monte Carlo results. And we see a very good agreement in both the lattice constant and the bulk modulus with experiment. One thing that was also very nice and important to see is when we compute the gap in the diffusion Monte Carlo for the bulk, we have a good agreement with what's known from experiment. So on that basis, we determined that the current methodology is working well, and we are justified in then moving on to looking at the 2D materials. Now I want to spend a moment talking about forces and geometry in quantum Monte Carlo, because as we proceeded with this investigation, we found out this was actually going to be very important. So one thing I would actually want to note right now is that actually forces are available in quantum Monte Carlo, and there's quite a few papers applying these particularly to molecular systems, but also in simple solids. So here's some work that we didn't do, but was done by Lai and Sepeli, looking at the phonon dispersion of metallic hydrogen running QMCPACK. So one can certainly do light element solids. However, there are some challenges. And that is, in the current schemes that are used and have been painstakingly developed over the last few decades, there's a requirement that the trial wave functions are systematically and consistently optimized actually in all their coefficients. And if one doesn't do this, one actually introduces an error, which then biases the force calculation. And we've investigated this. That's actually shown here in this lower paper, looking at, for example, carbon monoxide. And unfortunately, it does grow a little bit faster than we would like. So this solid red shows where the force goes to 0 in CO, but then with a particular choice of wave function that we haven't consistently fully optimized. And then if we look where the potential energy surface puts where the force should be 0, we see these don't quite line up. So that's an error coming in. So that's a concern, and we found it would actually scale with atomic number. And also we have a concern here about being able to do these consistent optimizations in large and complex materials. So this means there's more homework that we need to do as quantum Monte Carlo developers. The question is, what would we do in the interim? And that's the approach that I want to outline now. So we've developed a new line search-based strategy, which has been very successful in these 2D materials. So what we've developed is a surrogate Hessian parallel line search method, and this is published here and has got many more details than I can touch on in this talk, and many derivations developed by Juha Tihonen and Jaron Krogel. And there's two main ideas. So the first is that we're going to use a surrogate method, which will be density functional theory in our case, but it could be another method. And we're going to use this to pick reasonable search directions for our quantum Monte Carlo calculations, given some initial starting structure. So that's sort of shown here. In this plot, we have some initial structure, and we get search directions from the DFT. And then what we're going to do is, along these line search directions, we're of course going to do a line search with our quantum Monte Carlo calculations. So we're always going to use quantum Monte Carlo energies, and taken to the logical iterative conclusion, we will find the quantum Monte Carlo lowest energy geometry by this process. But then a key second idea is that with some knowledge of the potential energy surface, we can optimize the line search so that we use the cheapest and hence noisiest statistics that we possibly can while meeting the target accuracy that we're trying to do the optimization for. And so this clearly is going to work much better than a naive dense grid search, where we compute the potential energy surface with small error bars everywhere, for example. And this also works better than our previous Gaussian process-based approach. One thing I would note is, of course, is that this can work with any combination of electronic structure methods. They don't even have to be stochastic electronic structure methods. So here we're using DFT with quantum Monte Carlo. But if, for example, one had a new couple cluster implementation that didn't have gradients, one could apply it in combination with DFT. Or we could do a QMC correction of CCSDT, for example, or we use this with embedding methods. And in addition to the publication, all this is available open source at this GitHub link. So I'd encourage everyone to take a look if you're interested. So we've implemented this and actually applied it to multiple 2D materials now. I just show some results first here for the germanium selenide, because one thing that can come out of these calculations is we can plot sort of the energy surfaces and see how they compare, here in this case diffusion Monte Carlo versus PBE. So when we look at where the minima here are in this sort of 2-parameter scan, we see that the diffusion Monte Carlo minima is different from PBE, but generally the shape is relatively similar, and that means that the surrogate method is really going to accelerate the search in the diffusion Monte Carlo. This is actually being tested up to nearly 20 structural parameters, so it will work for a lot of the 2D materials that we are interested in. And for example, we've applied it to chromium triiodide in this publication. Here, where the diffusion Monte Carlo structures are now much closer to the experimental data. So what then do we find in germanium selenide? So here again, I've got a table of results, and we have 8 different structural parameters for this material. And again, we have a menu of different density functional approximations. I hope I have everyone's favorite included here. And here we have the diffusion Monte Carlo results. And the main point that I'd like to convey here is that we went looking to see if there was, any one particular parameter that DFT approximations were having difficulty with. And the answer in this material, at least, is no. There's just a range of subtle differences across all these parameters. So after obtaining the geometry with this optimization method, we went on to compute the optical properties. And this was an unexpectedly, at least I found it unexpectedly interesting. So at the bottom of this table, I'm showing the diffusion Monte Carlo results for a number of different excitations. I'll explain where they are in the band structure in a moment. So we have 3.2 for a direct, 3.6, but then another 3.2 for an indirect transition. And actually the quasi-particle gap is also very similar in this material. And so the interesting thing about this material is that when we plot the band structure, so this is a PBE band structure, so we know it's going to be too low compared to experiment, but should still give us a good guide as to where the bands go. When we look at this, we see there's a number of possible direct transitions and also indirect transitions, and they are all fairly close to each other. So actually, what we were then able to conclude was that, well, actually, germanium selenide has a strain-tunable direct to indirect gap transition. So by straining this material a little bit, we can tune these different excitations to be direct or indirect. So then, in addition to being sensitive to study in terms of theoretical methods, it's also sensitive in practice, and one might think to make a sensor, for example. Of course, one of our conjectures from this work is that likely other monochalcogenides will have similar sorts of properties due to combinations of both the structure of these materials and the electronic structure of the elements they tend to be made out of. So then, just to summarize this piece, we've learned that the optical properties of germanium selenide are both sensitive to the methods and the geometries, and the character of the optical properties in this material are very much tunable by small amounts of strain. We've also developed this method to optimize geometries that we can apply within diffusion Monte Carlo. And generally, we can also see that sort of the standard diffusion Monte Carlo approach is working well here. And this is the point we're actually going to come back to shortly. So I'd now like to move on to sort of the second part of this talk, which is much more sort of work in progress and a much more challenging material, that of lithium cobaltate. And actually, for more details on this work, look at this talk B48.8 presented by Anwar Banali earlier in the conference. I think we're probably all familiar with lithium cobaltate as being very widely used cathode material in lithium-ion batteries. And one thing we do know about this material from experiment is that it's a charge transfer insulator. And this, of course, poses a lot of problems for really all electronic structure methods because of the complexities introduced by the bands that are present around the Fermi energy. And so, for example, there's well-known challenges applying DFT to this system, and one generally has to sort of pick a compromise in the properties that one most wants to reproduce. In this study, what we wanted to do is just sort of bring quantum Monte Carlo to lithium cobaltate, and also, of course, see if we can compute the band gap of this material accurately. I'd like to take a moment to talk about how we obtain trial wave functions in quantum Monte Carlo, because I skipped over that earlier. What's now well established, particularly for metal oxides, is to do some limited optimization of the orbitals that we get from a particular DFT approximation by, for example, doing a DFT plus U or an exact exchange calculation varying the U or amount of exact exchange. And this actually works very well for a large range of materials that's been shown over the last decade at least. So let me show a sort of typical result here. So this is energy on the vertical axis, and this is U, so lower is better on this energy scale. And this was done for titania. And we see that actually for 3 different phases, we get a very nice U shape here, a nice single minimum. And also we see that, for example, the results aren't particularly dependent on the U around the minima. So here, the phase energy differences are all very similar, and it's only when we go to a much larger U that the results would change. We of course know to take the U here through the variational principle. Now let's look on the left at what happens in lithium cobaltate. So this is the same sort of plot. And let's look at PBE plus U. It looks like this. And there actually is a slight minima here, but it's much more shallow than we saw in titania or indeed even vanadium. And also the U that comes out is actually very large. Whereas in TiO2, it was sort of a reasonable U that you might use in a DFT calculation. Let me remind everyone that if one was studying cobalt in the materials project, for example, the U that would be used would be about 3. So here there's a hint that not enough physics is being captured or improved to improve the nodal surface for our diffusion Monte Carlo calculations. This is then evident if one goes on to compute gaps with these wave functions. And essentially, we found that the gaps are very trial wave function dependent on this material. And this is obviously something that we don't like. And we also saw then that the extrapolated gaps are much too high versus experiment. And just to show some of the dependencies, this is the diffusion Monte Carlo gap against U in a fairly large cell. So we would hope to be much closer to the experimental values of below 3 here. And we see that we have values 5 or 6 EV. And actually they get higher with these large U values as well. So this obviously isn't good enough. And what we thought to do was, rather than iterate through other possible choices, importantly, that would probably never give the exact nodal surface, or not necessarily even ever a sufficiently accurate nodal surface. What we thought to do here is use a different approach, and importantly, it's an approach that is potentially convergent. So if we pay enough in terms of compute time, this would give us steadily more accurate results. And that approach is the use of selected configuration interaction, in particular the CIPSI approach, to generate our trial wave functions. So let me say a little bit about the use of CIPSI. First of all, what is CIPSI? So CIPSI is one of the multiple flavors of selected configuration interaction techniques that exists. And it's a perturbative method for growing a multi-determinantal expansion, importantly given by a single convergence parameter. So you start with one determinant, you consider which possible excitations might contribute significantly to the ground state for example. And if they contribute significantly enough, you then add them into the wave function, and then you iterate, adding progressively higher excitations. And so this has a sort of simplicity that we find appealing. It was pioneered in particular by Michel Caffarel in co-workers, here shown for the water molecule. Here in blue is the diffusion Monte Carlo CIPSI result, and this was, I think at the time, the most accurate water molecule that had been computed, so potentially very, very accurate. And notice here that we're actually using the diffusion Monte Carlo to improve on the selected CI result. Actually, and since that work was done, we've actually had some collaborations. And so, for example, last year we were able to show that we could converge the ground state of bulk carbon diamond using this. And this is actually a system where the trial wave function is already very good with one determinant, but we were able to show we could improve it further and also, importantly, consistently improve the atom. One thing just to note in background is that we do have algorithms to evaluate the large numbers of determinants very efficiently, so we can use hundreds of thousands of determinants here. And here are some notes about the technical details for those who are interested. So what then do we find when we apply this in lithium cobaltate? Well, we only have results in small supercells so far, but already the results are very, very encouraging. So here I'm showing the energy on the vertical axis against the number of determinants, and notice the log scale. And at first we have the ground state, here in purple, and then above that in excited state. And actually one can see from the trend line that initially the gap here is going to be too high, or it's certainly higher than it eventually ends up. Then when we add a few thousand determinants, there's actually a large improvement in the excited state, much more so than the ground state. And then eventually they both start improving. So this is the capturing of dynamic correlation in the CI expansion. And importantly, these lines are starting to be essentially parallel at this point. And then also, this sort of shift in energy that we're getting through this procedure is about the right amount that we would like to see to get closer to experiment. So this is very encouraging, but clearly these are not in large enough cells already, and we need to be able to do the finite size extrapolation, much as we did in carbon diamond. Now, to make the link with the first part of this talk on germanium selenide, we've been able to apply a similar methodology where we use CIPSI to look at the band gap of germanium selenide and actually compare that with what we get from the single determinant trial wave functions that we use there. And importantly, we see actually very good agreement. So this actually tells us then that the trial wave functions were very good, and then that the agreement with experiment actually was not an accident in that case. So that's very encouraging. Now, one additional thing that we can get from this methodology, which I think is also very important, is that we have very easy access to things like the density matrix, and we'll be able to begin to analyze the sort of flavor and characters behind the excitations that we're looking at. So what's shown here is a plot of the difference between the density matrix for the excited state single determinant minus the multi-determinant done in the PBE basis. And if we look at the diagonal components of this, just here when we look at the unoccupied states in this case, we see there isn't just a single change. There's a large number of states contributing, at least in this PBE basis. And so we plan to continue this to analyze the character of each excitation. So then just to summarize all of this work, what we've seen, certainly in the last part of the talk, is that we can now begin to test the accuracy of trial wave functions and actually improve the reliability of gap calculations using these selected CI wave functions. We do need to make some efficiency improvements, though, going forward, and we have some ideas for this. For example, the use of natural orbitals, which should accelerate the convergence of the CI using optimized orbitals in the expansion. And then also we have recently ported this code to GPUs, so that should give a significant speed up as well. I've also shown you we've developed this surrogate Hessian approach, which we've shown is practical for optimizing the geometry of current 2D nanomaterials, and this can actually be used with any combination of methods, so I'd encourage everyone to try that out. And I hope it's really clear that combining both of these is going to bring us much closer towards our goals of having a standalone predictive theory. So on that note, thank you very much. I'll wrap up here. If you have any questions or like preprints of this work, please send an email to me. And also, fingers crossed, the chat will be working at this conference. Thanks very much.